Hello, everyone. Thanks for joining us today. My name is Natalie Frick. I'm going to be moderating our webinar today on recent research on the time-sensitive value of efficiency. And we have over 130 people that are participating in the call today on this very important topic, so that's great. And moving on to our agenda, today I'm going to give a quick overview of the research that we're going to talk about and explain some of our housekeeping, in particular with the webinar chat box. And then we'll hear 5 perspectives on the time-sensitive value of efficiency, followed by some Q&A. This is a really important topic to me and to everyone who's going to be speaking on the call today. Electric energy efficiency resources save energy and can reduce peak demand, and time-sensitive value of efficiency is becoming an increasingly important topic because historically the benefits and quantification of efficiency is largely focused on the economic value of the savings during the first year and the lifetime of installed measures, while less emphasis has been placed on the larger grid system and the timing of the savings. There's many applications for time-sensitive value or time-sensitive energy efficiency data, such as energy efficiency planning, distribution system planning, IRP, integrated resource planning, some of which we'll hear about today. And we're also going to discuss why we study and implement time-varying values and how to operationalize time-varying efficiency values. So for our webinar housekeeping, we're recording the webinar and we're going to post it on our website a couple days after we finish this. As you guys are all probably aware, you're in listen-only mode, so we won't be able to hear you if you're speaking. And so we do ask that you use the chat box to send us questions and comments anytime during the webinar, and you can direct your question to a specific author if you'd like. At the end, our speakers will be presenting for 10 or 15 minutes, and then we'll have moderated questions and answers following that based on the questions that you guys send us in your chat box. And this link is where our webinar slides will be posted in the future. So I want to give a brief introduction of our speakers. We have 5 folks. First up is going to be David Nemso, who's the director of the U.S. Department of Energy's Building Technology Office. As the director, David leads the BTO office in developing innovative, cost-effective energy efficiency research and development and other solutions for U.S. building technologies, equipment, systems, and whole buildings. David's made the promotion of traditional energy efficiency as well as dynamic, flexible, and time-sensitive energy efficiency, load management, and buildings to grid technology an office priority. After that, I'll be speaking on research that I've been doing at Lawrence Berkeley National Lab. I am a program manager there. And after me, Judd Boomhauer will be speaking. He's an assistant professor at UC San Diego in the Department of Economics. He's an applied microeconomist who studies environmental and energy economics and policy. And his research covers a range of topics, including electricity markets, oil and gas, efficiency, and economics of climate change. Following Judd, we'll have Ed Burgess, who's the director of Strategy Consulting's Utility and Government Practices, where he specializes in evaluation and design of policies and programs to advance deployment of distributed energy resources, demand-side management programs, energy storage, and grid integration of renewable energy. And finally, Snu Price is our final speaker. He's a senior partner at E3, has more than 20 years of experience supporting utilities and state and federal government clients with energy policy and resource planning. He's pursued a broad array of topics across the electricity sector, seeking large-scale, cost-effective opportunities and contributing insights, methods, and tools to the field throughout his career. So again, just a reminder, you guys are on mute. Use your chat box to send us questions, and we will be answering those during our Q&A period after everyone speaks. So I will now turn it over to David, and David, whenever you're ready, you can go ahead and I'll advance your slides for you.
Great. Thanks, Natalie. Can you hear me okay?
Yep.
Good. Thanks a lot, Natalie, and everyone for organizing and participating in this webinar. This issue of how do we analyze and value electricity, and therefore the efficiency of avoiding wasteful electricity use on a time-sensitive basis has become an important priority for the Department of Energy in general, and my office, the Building Technologies Office in particular. And I'll tell you about that, and then I'd like to also focus in a bit on how we're thinking about buildings going forward in the future to be a more dynamic resource than they have been in the past, and that one can't do that without a sense of their value over time. If you could move to the next slide. So this is just a reminder to all of us that buildings consume 40% of U.S. energy use, but since we're talking about electric efficiency here, let's look at electricity. It's buildings as distinguished from transportation or industry are consuming 75% of U.S. electricity use, and depending on what region you're in at peak, that is typically 80% or even more. So the total bill, not just for electricity, but for energy in U.S. buildings is $300 billion a year. Of course, much of that is wasted and could be saved through energy efficiency. And if you look at the pie chart on the upper right, that's looking at buildings, again, all types of buildings, commercial and residential, and looking at how they use it, and just focusing on two parts. The top wedge there, that dark blue, is for cooling, for air conditioning, and that's one that obviously is very time sensitive because people tend to use cooling the same time that their neighbor uses cooling. And then I won't talk about today, but on the left, that growing wedge called other or miscellaneous. I'm sorry, I see some of the, on the right, the graph didn't come out. Some of the color coding, the legend didn't come out, but that big gray on the left, that's 40%, is for other plug loads and other miscellany, which may or may not be time sensitive. Next slide, please. So those are the stakes involved here. You've all seen this graph. You probably all presented this graphic. The Thomas Edison, the early vision is on the left, the one-way power flow, and that on the right. This is just a reminder of where we, as a nation, and we at the department, are bringing the power grid to an interactive, dynamic, flexible grid in which there are many resources to produce power and many opportunities to consume it more intelligently, and not just one-way or even two-way power flows, but multiple power flows. Next, please. So we put a lot of effort in at the Building Technologies Office at DOE on, as I referenced earlier, making buildings, helping buildings to be able to be a more dynamic part of the power grid. So even as they consume that 75% of the kilowatt hours consumed in this country, generally that's been static. You plug something in, or you turn on an air conditioner or an electric hot water heater, and it consumes the number of electrons it needs to do the job. And we've worked in this office, and many of you have, to make the process more energy efficient in a traditional way, do the same job or better with fewer energy input. But now we're focusing a lot of our activity on making those loads flexible in a way that can be controlled by the end user, controlled by a building owner or manager, controlled by a third-party aggregator, and even potentially controlled by a utility or a grid operator on a dispatchable basis. And by making those loads more flexible, more ability to do that, we can shift load to improve. We can lower the total system cost, so that energy can be more affordable for American homes and businesses. And we can make the system more reliable, and we can help integrate renewables. That's our goal. And to be able to do all those things is a challenge. At the same time, buildings want to be buildings. They don't want to be somebody else's grid resource. They want to be homes or offices or hospitals or other things. So that's the challenge that we all face and that we're working on at BTO. Next, please. So we all know, if you look around your desk right now, you can look at how many devices there are, many of which are controlled. And again, they might have been controlled historically in a static way, perhaps now in a more dynamic way. And there are all sorts of ways. I won't go through these. I think it's self-evident. The real challenge going forward as we think about these flexible building loads and these grid interactive building technologies and capabilities is how do we do it in a way that meets occupant preferences, that's always the goal, but does it in a way that's efficient, that's interoperable, hopefully that's integrated with each other so that if, for example, right now you may well have an occupancy sensor that turns out your lights when it sees no no occupant in the room, but does it change the ventilation on your HVAC? Does it change as the light comes across your window attachments, automatically change to optimize daylighting or to avoid cooling? That's the capabilities that we're contributing to here with our research program and other programs. And again, that can be done because the occupant told it to do so, because the manager told to do so, because a smart algorithm that was programmed told to do so, or because the utility sent a signal saying prices are high or the system's stressed or prices are low, and go for it. So next, please. Of course, when I say go for it, we mean on a pre-cooling or temporary basis, not to be wasteful, but to shift load. So this concept, flexible building loads, which we often call grid interactive efficient buildings, and again, we want to keep that word efficiency in there. This is not just about load shaping and shifting. It's about making the buildings and the system more energy efficient in a grid interactive way. We're looking at four goals there that you see in that circle diagram. Energy efficient, of course, going clockwise. Smart, and I'm using smart to mean has the microprocessors, the algorithms, the capabilities to be able to make smart decisions. Connected, I mean two ways. I'm sorry, I didn't fix the graph here. Connected means two things to us. Connected to the internet, so that those smart technologies and those remote opportunities can be taken advantage of, and we can control building load in a way to be more productive, more comfortable, more efficient through smart controls and through algorithms. So connected to the internet, but of course connected to the grid. So that is, of course, it's connected to the grid now, but again, in a dynamic way, not just a passive way. And finally, flexible, which I've already described. Next, please. The next slide, please.
Sorry, I'm trying to make it advance, but
okay.
It is hung up for some reason.
All right, thanks. Sorry about that. And the firewall, the reason I have to ask for this, our firewall at DOE, I won't even talk about cybersecurity today, but our firewall is very robust here at DOE, and we had a little trouble with the controls.
Sorry, Kristen, can you advance the slides? I just got kicked off of the webinar. I apologize.
No, we're good. Kristen, yeah, slide 14 is just where we want to be. Oh, I'm sorry, going forward, yeah. So look, I stole this slide, as you can see, from PG&E. Thank you, Jan Berman. And she did present it at a DOE event, so it's public domain. But seriously, these are two buildings, and you can see from the photo on the surface, they're very similar, modern, highly efficient, highly in fact, I think they're both zero net energy. They have a lot of solar. They have a lot of efficiency. They're excellent workspaces and public spaces. The difference is, and those load curves at the bottom that you see below the two buildings, those are just representatives. They're not actual data from these buildings, certainly, but they're representative. If you have a building that looks like the load curve on the bottom left, you can see, right, that the organic load from the different end uses in the building are in that yellowish gold color, and you can see the PV, and you see where I'm going with the story in terms of time of day and how they do and don't align. But as the utility perceives that, as PG&E in this case, or any utility perceives it, they see a problem, right? You can call it a duck curve. You can call it an inflexible load. You can call it an opportunity where load and supply either no longer match up so well, or the utility doesn't have the certainty that they'll match up and has to deploy its resource properly. If you look on the right, a very similar building, but with energy efficiency and demand response, and it could also be storage, of course, but with flexible loads, it can shift the time of consumption to better reflect where the solar is and to create a net load curve, which is what you can see with that black line. That is easier for a utility to meet, and not just easier for the utility, but more affordable to society. And affordable is defined broadly in terms of the total cost, economic cost, but you can see it also helps integrate solar. So those are the goals. We're trying to get buildings to be more like that load curve on the bottom right. Next, please. So this is a summary. I'll let you read for yourself. Again, at BTO, my office, the Grid Interactive Efficient Buildings portfolio, we're doing 4 basic areas. One is how do you value these services? We're working very closely with Natalie and the team at Lawrence Berkeley National Lab, as well as other national labs and other resources. Technology, all right? We just learned something about valuation in the top left. What are we going to do about it? You can see our little icons, connected LED lights, connected water heaters, white goods, et cetera. And how do you advance those technologies so they're efficient and flexible and controllable? Going bottom left, optimization for GEB. What does that mean? That is government speak for how do we optimize all these things? We're trying to accomplish multiple goals for the building, for the grid, for the national economy. So how do we optimize across these multiple goals? And finally, validation. It's important to do this at our desktops. It's important to do it on a spreadsheet. It's important, though, to do it in a controlled laboratory environment. Berkeley has one of the best in the world. So does Oak Ridge and NREL and other national labs. But we also need to validate these technologies and these practices in the field too, because of the complexity of buildings and the complexity of human needs to get the energy services they need. Next, please. This is just a teaser for today's show. If you think all energy efficiency is equally valuable, stay tuned. In an hour and a half, you will no longer think that. And this is just a teaser. I won't discuss it. This is what our speakers today will. So let's keep going. And I want to mention in our portfolio with the next slide before I wrap up at BTO. We can jump one more slide. This is one of many projects we're working on. Sorry, one back, please, number 17. This is just one of many projects we're working on that we're just getting going now, working with, again, National Renewable Energy Lab and Berkeley Lab, as well as in partnership with the Northwest Energy Efficiency Alliance and EPRI and other players, is to look closely at end-use load profiles. And you can ask, why do we need to profile end uses like refrigerators and lights and air conditioners? Didn't we just do that 30 years ago? And obviously, sincere in that joke, the data is getting a little old in many parts of the country. We have very good data, but it's getting a little stale and practices have changed. So this is a very exciting project to do some rigorous analysis over the next couple of years in this area, which will obviously feed into the time-sensitive valuation. And then quickly, the next slide is a summary of what I've been saying. It's a bit of a sales pitch with little graphics to prove that flexible building loads and grid interactive building loads will contribute to these important goals of affordability, grid reliability, easing congestion, shaving peaks, shifting, better quality services for home. We haven't even talked about how these smart technologies make life and workplaces better. They make the air cleaner. They give customers and users a lot more choices than they had. And finally, a slide with some of the team at BTO who's working particularly on this issue of time-sensitive valuation. So you have the contact information, I think, through the Natalie's email. But if not, this is who we are. Jack Mayernick is at NREL and at BTO, Monica Newcomb, and myself. So please reach out to us. Thanks, Natalie. That's BTO.
Thanks, David. We did have a question come through about what GEB stands for, or GEB, and it's Grid Interactive Efficient Buildings.
There is a reward for a more poetic name. Thank you.
Thanks, David. Okay, so my name is Natalie Frick. I'm with Lawrence Berkeley National Lab. I'm going to talk about some research that my colleagues and I have been working on time-varying value of efficiency. And the first report that I want to talk about is, Kristen, can you advance my slides for me too, because it appears that I'm still having problems with that. So if we could go to the next slide. There's a picture of 2 reports on it. One is for a report we did in 2017, and another one is from a report that we did in 2018 that was technical assistance from to the Michigan Public Service Commission. And I'm not seeing that the slides are being advanced. So if someone can move to slide 22, that would be helpful. And
Natalie, we're on slide 22.
Okay, great. Sorry, I'm not seeing that. So we have a variety of motivations for studying the time-varying value of efficiency, primarily to advance the consideration of the value of efficiency measures during times of peak electricity demand and high electricity prices, and to increase awareness of available end-use load research and its application to time-varying valuation of energy efficiency and gaps, and the need for research on energy-saving shapes. Next slide. I did want to mention we had 3 goals on that last slide with our research to calculate the time-varying value of efficiency for 5 different regions, to recommend methodologies to appropriately value efficiency for meeting peak demand, and to consider changes to efficiency valuation methodologies to address the changing shape of net load. And then moving on to the next slide, thank you. Our approach was the same here for both of our studies. We used publicly available end-use load shapes, and avoided costs were available for 4 states and 1 region for 5 different energy efficiency measures. We chose these 5 measures because we wanted to look at electricity consumption for both summer and winter peaking systems. So we looked at residential cooling and heating. We also wanted to look at commercial and residential lighting, since they've historically made up such a significant portion of energy efficiency portfolios. Our exit sign was our proxy for what a value of energy efficiency is that's on all hours of the day. And we chose 5 different regions that were geographically diverse and had both summer and winter peaking systems, and were part of ISOs and RTOs and vertically integrated utilities. If we could move on to the next slide. We used 1 of 2 different methodologies to calculate the time-varying value of efficiency. If we had hourly avoided costs and end-use load shapes, we used those, and if we didn't, we used information based on the seasonal system peaks, coincident factors, and diversity factors to determine the peak and off-peak savings, and then we applied the seasonal avoided cost to the savings. So if we had it, we used 8760 data. If not, we converted data to meet that. Next slide. So this is a graphic of the system load shapes over the course of the year for our 5 different electricity systems. The last one, the gray line that says CE/DTE, is Michigan. And so you can see from this chart that all of our electric systems that we looked at are summer peaking systems, because they all have their highest point in July, August, except for the Pacific Northwest, which is up around 100% in the December and January timeframe. So the systems are peaking at different times for the Pacific Northwest and the rest of the electricity systems that we looked at. And this is one of the underlying factors that drives the value of efficiency. Next slide. This is a slide that David showed in his presentation as well. This is the analysis that came out of our work for our 2017 report. And this shows the time-varying value of the 5 different measures in Massachusetts on a summer day. And so you can see that residential air conditioning, that top pale blue bar or chunk of the bar, is for distribution. And the distribution costs along with the capacity costs are really what drove residential air conditioning value in Massachusetts on the summer day. So the different measures have different values. And if you looked at the winter slice of this data, it also looks different, and there isn't as much value for residential air conditioning, obviously. So moving on to the next slide. This is a summary of all of our results. So what is on, the axis is a ratio of all the total utility system value of savings as compared to the energy-only value. So the total utility system value is distribution and generating capacity and demand reduction induced price effect, if applicable, which it is in New England, carbon dioxide or other air quality, air emissions values. Whatever is being included publicly in avoided costs is part of that total utility system cost as compared to the energy-only value. So as you can see, we have very high ratios of total system value to energy only value for the residential air conditioning in California and Massachusetts, meaning that those measures have more value than just the energy only, and that's important because we've often only been considering energy only values. In the Northwest, you can see that the residential air conditioning, that's the first set of bars. The middle blue, kind of dark blue bar is residential air conditioning in the Pacific Northwest, and it's right at 1.0 because the system value and the energy value is the same because it's a winter peaking system, so there's not additional value being generated to the system at that point in time. The last three chunks of bars are all for Michigan that use different approaches, some of which I will discuss in the upcoming slides. And there's lots more research available on that, which we can talk about in Q&A or in the future. So if we can go on to the next slide, I want to talk a little bit, I want to go through 3 or 4 conclusions and some examples of it pretty quickly. So one of the conclusions that we found that was important is that publicly available end-use load and energy savings shape data is pretty limited and concentrated regionally and needs to be expanded. And this is one of the reasons that accurate load shapes are really important. So what this chart shows on the left is that different load shapes from different data sources produce different outcomes, which isn't too surprising, but they can be extremely different. So the tallest bar for this chart on the left shows that simulated load shapes may not represent diversified loads, and the value there for residential air conditioning is $500 for the levelized total utility system value, as opposed to load shapes that are not based on metered data, also simulated but more diversified, are down around $200 per megawatt hour for the levelized total utility system value. And then on the right side, our residential lighting chart shows that statistically representative metered data provides a more accurate representation, and what we have on the far right bar is some metered data from a similar latitude as what Michigan is, and that shows the value, you know, around under $70 of value, as opposed to this modeled data, which is pushing the value of residential lighting up to $90. And I'll talk about this more on my next slide, which shows a graphic representation of what, for that residential lighting example, the metered load shape, you know, shows a typical residential lighting where lights go off at the beginning of the day, which is hours across the bottom of my chart. People wake up, they turn their lights on, you know, 7 to 9 a.m. People go to work, they turn their lights off, and then they come home and turn them back on. So pretty standard residential lighting shape. That's producing a value of about $56 a megawatt hour, as opposed to some of the modeled energy efficiency from residential lighting that we looked at when we were studying our Michigan, when we were doing our Michigan work, which produced a value of $75 a megawatt hour. So the modeled data was not as accurate as the metered data, and is producing different values, and that's important because if you're planning your utility system around these values, or planning your peak reductions around these values, you need to have them generating the appropriate values. So moving on to the next slide, one of the other conclusions is that all avoided costs matter. In Georgia, we didn't have as much publicly available avoided cost data as we did in other regions, and this shows up because we only have 2 different colors in this stacked bar chart, which are capacity and energy, and none of these other values were publicly available, so it's under, Georgia appears to have less value for efficiency than it does based on conversations with the utility in Georgia, what they use in their utility system planning, because they do have values for distribution and transmission. They're just not available publicly. And so when you start comparing across the country, if you're not looking at all of the values together, you're going to have skewed outcomes, which may show that values are higher or lower when that's not necessarily true. It's just based on the data that's available. If we go on to the next slide, one of the other conclusions that came out of the research is that the underlying electricity system shape is obviously very important. That's what's generating the avoided cost values and utility system values. And as many of us are aware, those values are changing. This graph is from some work that E3 did for PG&E, and it shows the difference from 2019 to 2024 of the increased use of distributed energy resources on the grid and how the anticipated difference in load shape for utilities and for PG&E in this example. And was an important conclusion because the electricity system shape is changing in ways that it hasn't been historically, and the data that we're using to estimate the impact of efficiency measures on that peak will need to be updated periodically to make sure that we're giving it appropriate value at the times when the system is at its peak. So that was a pretty big conclusion that we came to. If we go to the next slide, this is another example of that. This is a duck shape from some work that Jim Lazar did for RAP, and this really represents the opportunity for energy efficiency with this changing electricity shape. If we can use energy efficiency measures to reduce the ramp of the as variable generation winds down and people start consuming a lot of electricity as we go up that steep ramp. If we can use energy efficiency to dampen the ramp some, it's going to generate a lot of value and also make the electricity system less expensive and easier to operate. So, as the system shape changes, there's still opportunities for efficiency. And moving on to the next slide. I think this is my last example of some of the conclusions we came to, and this is about saving shapes. And a saving shapes is the difference between the hourly use of electricity in the baseline condition and the hourly use after installing an energy efficiency measure. For example, the difference between hourly consumption of an electric resistance water heater and a heat pump water heater over the course of the year. So in other words, the timing pattern of savings from the substitution of a more efficient technology doesn't always mimic the underlying use. And if we can go to my last slide, this is a visual display of this idea that a savings shape may not align with an end-use load shape. And so this is data on the top from Massachusetts and on the bottom from the Pacific Northwest. The green line in both of these charts is from a heat pump water heater, or excuse me, a heat pump heater, and the red line is electric resistance heat. So you can see that the shape is different from electric resistance heat, which is typically what's modeled for the end-use load shape, than it is from the heat pump heater. And if you're planning your electricity system around these peaks, your savings may not align with what you've typically thought the consumption looked like, which is going to alter the value both to the electricity system and to the consumers. So this is just more of the same in regard to why end-use load shapes are important, why the time-sensitive value of efficiency is important, and why we continue to be interested and want to make sure we get these numbers correct. So I will stop there, and I will hand the controls over to Judd to talk about his work. Thank you.
Great. Thank you, Natalie, and thanks everyone for having me on this call. I'm excited to tell you about some work that I've recently been doing with my colleague Lucas Davis at UC Berkeley and the Energy Institute at Haas at UC Berkeley. This work was supported by the California Energy Commission, so we're very grateful for that support. And I think my colleagues on the webinar have done such a great job of setting up the question that I can actually skip some of this introductory material. So I'm gonna skip the first few slides and go right to the research questions. So we think what we're gonna think about in this paper is we're gonna use smart meter data, highly granular customer level electricity consumption data to see what we can learn about time-sensitive values of energy efficiency. So there are basically two things that we do in this project. The first thing is that we use smart meter customer data to think about when energy efficiency upgrades deliver energy savings. And then we use electricity market prices to think about the value of each unit of electricity savings at different times. And our ultimate objective is going to be to calculate estimates of how the value of different energy efficiency investments change after we account for time-sensitive values. So in many ways, this is going to be highly complementary with the work that Natalie just showed you. I think the piece that differentiates this is that we're going to be working with individual customer level actual consumption data. So that's where I'll I'll spend most of my time. Of course, the reason that we're able to do this study now and that we couldn't have done it 10 or 15 years ago is because we have had, over the past few years, a rapid rollout of customer smart meters. So today, this slide goes through 2015, and this is even more exaggerated today, but we now live in a world where a large fraction of electricity customers have their consumption metered at an hourly or sub-hourly level. Specifically, what are we going to do in this paper? We're going to look at, the first thing we're going to do is we're going to look at a large sample of Southern California Edison customers who participated in an air conditioner rebate program. So we're going to be thinking about households who replaced a central air conditioner with a new energy efficient central air conditioner. We're going to calculate energy savings by hour of day and season of year for that air conditioner replacement. And then we're going to value those savings, as I said, using energy prices and capacity market prices. And I'll tell you how we think about that calculation. We're going to find that accounting for timing for residential central air conditioners raises the implied value of the air conditioner program substantially by about 40%, depending on how we do the calculation. And then the last thing we'll do is we'll then use engineering estimates for savings profiles for a number of other energy efficiency technologies to think about how what we call these timing premiums compare across different energy efficiency investments. That last part's going to be a little overlapping with what Natalie showed you, so I may go through that quickly. I'll skip this for time, but I'll just say that we, of course, we build on work by a bunch of other academics who've come before us and have done high quality research. And I'll also go quickly through this, but the particular energy efficiency program that we're thinking about is Southern California Edison's Quality Installation Program, which provided rebates of $500 to $1,100 to households to install an energy efficient central air conditioner. So the data set that we're going to use for the main component of this paper includes 6,000 households who replaced 6,000 households who got a new air conditioner, 150,000 households that did not participate in the rebate program. We're going to use them as a comparison group in some of our regression specifications. And the things that we know about these households are their 9-digit zip code and their hourly electricity consumption from 2012 to 2015. I'll skip the details of the regression. I'm happy to talk about this in the Q&A, but I'll just say that we measure energy savings for participating households using standard program evaluation techniques. Essentially, what we're going to do is we're going to measure the change in household electricity consumption after installation of the new central air conditioner. And the fact that we have highly granular electricity consumption data and the fact that we're able to compare consumption to a reference group of non-participating households makes us pretty confident that we're able to control for potential confounders like weather and seasonality and electricity consumption. So let me tell you quickly sort of what happens to overall electricity consumption when households get a new energy efficient central air conditioner. In the summer, hourly electricity consumption falls by about 0.2 kilowatt hours per hour. In the winter, we don't see much change in electricity consumption, which is not surprising. And overall, depending on exactly how we want to set up the regression, we find that getting a new central air conditioner saves this sample of households about 400 kilowatt hours per year. In sort of the typical literature on energy efficiency program evaluation, this is where the study would have stopped. We would have said, okay, this thing saves about 400 kilowatt hours a year for this type of customer. and we would have valued that with some sort of average price and come to a conclusion about the value of the program. We are going to push further and think about time-sensitive valuations. I'll skip this next slide mostly for time, but I'll tell you one thing that makes us pretty confident that we are actually measuring the effect of air conditioners as opposed to the effect of some other investment that the households might happen to be making at the same time that they're getting a new air conditioner, is that we essentially only see energy savings at high temperatures. So this figure is showing you the change in electricity consumption, or you can think about this as the treatment effect of getting a new air conditioner, and that's basically zero below about 70 degrees, and then sharply increasing treatment effects, so big decreases in consumption at high temperatures. This is sort of our first main result. This figure is showing you our measured electricity savings by hour of day and season of year for the households in our sample. So let's start with these markers that are labeled July and August. Again, this figure is showing you the 24 hours of the day on the horizontal axis, changes in electricity consumption on the vertical axis. So what you can see is that during the summer months, during July and August, as you would expect, central air conditioner upgrades save a large amount of electricity in the mid and late afternoon. And I think, again, kind of unsurprisingly, during the other months of the year, at least in this part of California, we don't see much effect from air conditioner replacement. We can get even more granular with our estimates. So the left panel in this figure is showing you our estimated savings profile, again by hour of the day, and then there are 12 lines in this figure that correspond to the 12 months of the year. So the summer months are in red, the winter months are in blue. In the paper, we talk about some ways that this savings profile is similar to what engineering predictions would give you for electricity savings, and we also talk about some interesting differences. For example, we find that essentially all of the savings are coming in the summer, while engineering models, at least the one that we think about most in this paper, imply meaningful savings in the afternoon and the winter. We also find a larger share of savings coming overnight and in the early morning. So this is just sort of interesting, although on the whole, I think what we conclude is that the estimated savings profile and the engineering predictions are relatively similar. So far we have highly granular estimates of electricity savings. The next thing we want to do, and I'll talk about this quickly, is we want to think about how to value each unit of electricity savings at different times of day. So we're going to bring in wholesale electricity prices. We're also going to bring in capacity prices. And we're going, in the paper, we have a section where we think about how to allocate those capacity prices to different hours of the day. Because obviously we're able to observe wholesale electricity prices in real time. Capacity prices we only observe at a monthly or annual level. So there's some work in the paper to translate those to hourly values, which basically involves assigning capacity value to the highest demand hours every year. I will just quickly show you roughly what things look like in a couple of different markets. In California, in February, we find a relatively small peak in values in the late afternoon after we think about capacity value. And in August in California, we find much larger value peaks in the afternoon. So the vertical axis in these figures now is the value of electricity, or you can think about this as the value of avoided electricity consumption in dollars per megawatt hour. And the different colored lines in the top panel are showing you different ways that we use in the paper to assign capacity value across hours, but the story is relatively similar. The bottom panels are the ERCOT market. ERCOT is a little easier to think about. It's an energy-only market, so we don't have as much work to do in terms of capacity values there. But again, you can see that the price profiles in ERCOT are broadly similar to California. Putting the savings and prices pieces of our paper together, we find that during the summer, the correlation between high energy savings and high energy prices is quite pronounced for central air conditioners. During the winter, that correlation, of course, doesn't exist as much because essentially air conditioner investments just aren't delivering any savings at any time in the winter. So that's a flat relationship. That was the graphical way of putting those things together. If we put those things together quantitatively, I'll sort of skip to the punchline of this slide, which is the bottom row here called timing premium. After we account for the hourly value of electricity savings, only using energy prices in California, we find that the air conditioner is about the air conditioner upgrade is about 12% more valuable than it would appear using a naive average value of electricity. Once we include capacity values, that timing premium increases to about 40%. And again, the timing premium is what we call the difference between the value of the program after accounting for time-sensitive value versus before. I'll go relatively quickly through the rest of this talk since I think we're running a little behind. But I'll quickly say, of course, we all know that the price shape in the market is changing as we move to a world with higher penetration of renewables. So the periods that have high electricity prices are shifting. And if we use forecast future electricity prices to calculate timing premiums, we find that this becomes even more important, so that accounting for time-sensitive values changes our conclusions even more. I'll skip the next two slides, which show you load shapes for different energy efficiency investments from the engineering literature, and just wrap up by showing you sort of a summary slide at the end of the paper where we say, let's think about a bunch of different potential energy efficiency investments that all have different savings shapes. And let's think about 4 different electricity markets where we've tried to account for energy and capacity value where appropriate. And just think about how accounting for time-sensitive value changes the implied value of each of these energy efficiency investments. So residential air conditioning in the top row here becomes substantially more valuable in California and Texas after we account for time-sensitive value. In New York, the importance of the effect of accounting for time-sensitive value is a little smaller for the reasons that Natalie talked about, that this is essentially a place that frequently experiences high electricity prices in the winter. The other thing I want to point out is that most other investments have smaller timing premiums than air conditioners on the residential side, which is not surprising. There are some small negative numbers in this top panel, which essentially means that these are investments that actually look a little bit less valuable after you account for time-sensitive value. So these are things that actually slightly seem to deliver electricity savings at disproportionately low value times, so at night or possibly in the winter in a summer peaking system. And then in the bottom panel, we also find that accounting for time-sensitive value is also quite important for commercial and industrial energy efficiency investments. So I think I've used up my time, and I will pass the microphone to our next presenter. Thanks for your time.
Thanks, Jed. Hi, everyone. Ed Burgess here from Strategy Consulting. And today I'm just going to talk about some analysis that we did, and the title is "It's a Duck Curve Eroding the Value of Energy Efficiency." First of all, a little background on Stratogen Consulting. We provide some technical support to public, private sector, and NGO clients on state-level policy and regulatory issues with a focus on the power sector. In addition to energy efficiency, some of the issues we focus on include solar PV, energy storage, electric vehicles, rate design and cost of service, integrated resource planning, and interactions between distributed resources and wholesale markets. Recently, we conducted some analysis for the Southwest Energy Efficiency Project, one of the regional energy efficiency organizations, to support their efforts in proceedings before the Arizona Corporation Commission. And a portion of this analysis serves as the basis for my talk today. Just a quick overview for today's topics. I'm going to cover a little bit on energy market trends in the southwestern U.S., some of the recently proposed changes we've seen to utility demand-side management programs in the region, and then some of our analysis on the implications for current and future DSM cost-effectiveness. As I'm sure everyone knows, there's been pretty significant deployment of solar PV resources in the southwestern U.S. Today, over 10 gigawatts of large-scale solar are in California, and several gigawatts more are behind-the-meter solar. Recently, the California Independent System Operator reached an all-time maximum of serving over two-thirds of its load with renewable resources during a brief interval of about two-thirds of that coming from solar PV. And of course, this large amount of solar PV has led to the infamous duck curve. Here's an actual example from April of this year, showing the system load in green over a 24-hour period and the net load, or load minus renewables, in purple. And you can see both the drop in net load during the midday when solar is at its peak, also known as the belly of the duck, and then the steep ramp up in the evening as the solar production drops off. This drop in the net load, of course, tends to suppress wholesale energy prices during the midday. Here's another snapshot from a recent summer month in July, and you can see that I just note here that the scale is actually about 2 times the previous chart. So overall, quite a different picture with a more sustained high load throughout the day and higher corresponding energy prices. And these dynamics have an impact not just in California, but also in the surrounding regions. As the wholesale markets evolve in the West, we have already significant exposure to California market prices. This includes places like Arizona, which was the focus of our analysis, and Arizona Public Service in particular. Many utilities, including APS, are already part of the Western Energy Imbalance Market operated by the California ISO, which is a real-time only energy market. And then some are also exploring day-ahead market offerings as well. I may skip this one in the interest of time, but I just want to point out that Lawrence Berkeley Labs completed some very good analysis on the impacts of renewable energy on wholesale market prices, and I encourage you all to look at it. The main thing I want to point out is, of course, we're now observing a higher frequency of low and negative pricing in the California ISO due to a number of factors, but one of those factors, of course, is this increase in renewable energy. Mostly, this occurs in the real-time market, but occasionally it's also occurring in the day-ahead market as well. Here's a snapshot from the day-ahead market in April, showing negative pricing on some of the low load days indicated by the arrows. So these trends towards low and negative energy prices have led some utilities in the Southwest to propose fundamentally different approaches to their demand-side management programs. This slide shows an excerpt from APS's proposed 2018 plan. On the left is a chart showing the real-time prices in April, indicated by the black line. Notice that some of the prices in midday are in fact negative. And then also the load shape for some selected DSM measures shown by the colored bars. And you can see there's some overlap during this month between the energy efficiency measure savings and the negative prices. And on the right is a statement from the plan that says, continue to promote EE savings during the middle of the day when prices are shown as below can actually harm customers by limiting the ability to take advantage of negative pricing. A new opportunity now exists with DSM to strategically build load in the middle of the day through load shifting, vehicle electrification, and reverse demand response. So this is a very different, approach of what we might normally think for utility DSM programs. And In addition to that, as a part of its integrated resource planning process, APS proposed very significant reductions in the energy efficiency programs in the near future, with planned savings being reduced, on the order of 85% in future years. On the other hand, APS is also experiencing significant demand in the summer months from June to September, which correspond to higher energy prices, and this is an 8760 hourly profile of their load in 2017. You can see that they actually reached a record peak in June of 2017, suggesting there could be a growing need for new capacity. This suggests that there is actually significant value to EE during certain times of the year. So the fundamental question is, what is the value of energy efficiency now and going forward? On the one hand, we've got reduced value of EE, if savings occur during the belly of the duck when there may be lower negative energy prices, but we also have increased value of EE during peak load hours of increasing peak demand. So we set out to sort of do some more analysis on this, and we took a look at 8760 hourly market prices, both recent historical prices and forecasted future prices. And then we also took a look at the 8760 hourly load shapes for some different measures, as well as a aggregated portfolio of DSM measures. And then we combined these two to come up with a time-weighted avoided energy value for the DSM measures. I just want to point out this is really just meant to be first-order look at the energy value. We didn't take a look at some of the other value streams that have been mentioned, like capacity, maybe avoided T&D, or environmental costs. But this is just meant to get a sense of the time value just based on the energy alone. So here's just an example of some of the recent market prices for APS in 2 different months, showing the hourly average across the day. And here is a picture of some of the DSM measure load shapes, just to point out that some measures, such as the commercial lighting shown in gray there, have a stronger overlap with the typical solar PV output, and others, such as perhaps water heating or cooling, don't have as much of an overlap with that in this showing an off-peak or non-summer load shape. Like I said, we also looked at some forecasted day-ahead market prices, and so these are projections of what the future prices might be. This chart shows a price forecast for a typical day in each month, both for current year 2017 and a year in the future, 2025. This forecast was done under the assumption that California would reach a 50% renewable portfolio standard by 2030, which was the prevailing law at the time. That's since been surpassed, and now they've accelerated those targets, but this is what we looked at in our analysis. And so just wanted to summarize the results of this here, and to walk you through this, each of the colored bars is a time-weighted energy savings for a different year, with the leftmost, the light blue, representing the actual 2017 market prices, and the others representing the projected future prices. Each cluster is of the bars is a different measure or portfolio of measures. And the green line is a recent portfolio level cost for DSM, APS's DSM portfolio. And like I said earlier, this doesn't account for any capacity or other non-energy benefits. But the things that, the conclusions that we draw from this is that each of these measures by our evaluation, looking across the entire year and in the future years, each measure appears to produce robust energy savings at least through the next decade. This is probably true even if some of these measure costs were to increase over time. And also the savings, they do begin to fall off under the very high renewable energy penetration scenarios as we get farther into the future, and we have more zero marginal cost energy on the system. But also the effects are very different for each measure. As we might expect, the commercial lighting doesn't perform as well while the residential cooling performs very well under all these conditions. So, thinking a little bit more about, this could guide our thinking on how we think about DSM going forward and which measures have higher or lower value going into the future. So just a few conclusions. The increased renewable energy penetration, especially solar PV, which has a notable diurnal cycle, is introducing a new time dimension to the value of energy efficiency savings. And the marginal value of energy efficiency savings is affected by increased solar PV penetration. These effects have been pretty limited to date, but they're growing quickly in some regions. And it's important, I think, for everyone to think about a full annual or multi-year perspective when evaluating the total impact of solar PV or the duck curve on energy efficiency measures, to avoid sort of cherry picking data or just looking at certain months out of the year. The time-weighted analysis of the energy efficiency measure values, it's going to be increasingly important as more renewable energy comes on the system. But for the time being, I think that the existing approaches and portfolios we have appear to be fairly robust, even under some of these high PV areas. We'll of course have to adjust over time to reflect the changing grid needs. Importantly, to conduct this evaluation, will be very key to have robust data on both the EE measure load shapes, but also the projections around wholesale prices, ideally on hourly resolution, and having them be regionally specific. And that will help our planning and evaluation going forward. So with that, I thank you, and happy to turn the rest of the time over to Stu Price.
Thank you. Hello, everyone. I'm going to just give a quick overview of time-specific valuation in California. I think I have the honor of running the anchor position of this relay, so deep breath. We're almost there. I'm going to take about 10 or 15 minutes, and then we're going to have an opportunity for questions. I've seen a number of questions in the Q&A, so I'll try to cover those off as we go, and then we can have a more open discussion as we get there. Talking about time-specific valuation in California actually gives us a lot of history. California has been using hourly estimates of value for efficiency for nearly 20 years, and I'm going to sort of cover off where California has been using them and why. And I think the tenor of some of the questions in the Q&A is around, well, is it worth it to take on the additional complexity? I can see how it can be done. I can look at the coincidence of the loads, et cetera, but is it worth that additional complexity? And I think for some applications, the answer is definitely yes. And then I thought I would look a little bit into the future of what are the emerging aspects, what are the new types of analyses that we're doing that are using time-specific values. And I think that the takeaway message should probably be pretty clear by now for everyone. I mean, what we're doing is decomposing the value of the grid. So, if we're using an average annual value for energy, that's exactly that. It's an average. And so for some evaluation, for some types of measures that really reduce load during the higher than average hours, you get more value when you decompose. And really that is the takeaway message. And then the trick lies in, well, how do you do that easily, repeatably, reliably, all that type of thing. So the first project where California, at least that I'm aware of, where California really took on time-specific valuation was in the Energy Commission building code. We started a project that was funded by PG&E and later picked up by the Energy Commission in 1999 to use hourly evaluation of all of the buildings in new construction. And essentially what it does is it gives a assessment of all of the types of features that you might build into your building, and it gives it its appropriate value. So the initial focus in California in 1999 was on air conditioning and shell. And by looking at time-dependent valuation, we're able to really show a lot more value in insulation and air conditioning performance. And that was the driver for it. I think there was a question maybe by Rick on, well, hasn't California looked at energy from a financial perspective? And that is what time-dependent valuation did. So when the Energy Commission adopted TDV for state energy standards, before that it had been a source energy kind of evaluation for building performance. And TDV really, although it's reported in terms of a BTU type of metric, is really looking at the financial performance of the building. The second major place where California took on time-dependent valuation or time-specific values was through the CPUC energy efficiency cost-effectiveness proceeding. And that we started work on in about 2003, finished in 2004. So if you remember, at this time, California had its energy crisis. We were having rolling blackouts. We were having a lot of problems with peak capacity. And so by looking at time-specific value, the PUC was able to focus a lot more of the energy efficiency dollars and dollars spent on looking at the peak question. So just to pull up a blast from the past, I went back and pulled a slide from a PUC workshop circa 2004. And it looks not unlike a lot of the other pictures that we were seeing before in earlier presentations. We've got air conditioning on the left, and we used the exact same basis for values, but looked at air conditioning via an hourly specific value, a time of use average, and an annual average. And so for air conditioning, you just get much more value when you go to hourly because it picks up all of the correlation. California summer peaks, especially in 2004, really driven by air conditioning. So you get way more value for AC, which allows you to justify spending a lot more on measures that reduce air conditioning. Refrigeration was sort of our exit sign. It was the flat, the flat shape, and it doesn't matter. If it's a flat shape, it doesn't matter whether you're doing hourly, TOU, or annual. And for outdoor lighting, actually, outdoor lighting was efficiency, was saving energy at lower cost times. So, I think a lot of these still hold, and then the question of sort of whether it's worth it. Well, if you're really focused on improving your air conditioning program, the answer is it probably is worth it. The avoided cost estimates that are hourly in California have continued to evolve since 2004. This table shows each of the components that we use, and each of these are disaggregated by hour. The other dimension that we haven't talked a lot about is that they're also all decomposed by area. So we have area and time-specific value components for each of these. I'm going to touch on a few of them just to show how they look and sort of what some of the considerations are. But I think that the overall message is that it's actually fairly doable. The inputs that we get for long-term forecasts of each of these really come from the resource planning and the resource planning type of analyses that the state is doing. So they're sort of a natural output of the supply side assessment. And California is moving towards integrated resource planning where we've integrated the demand and the supply side. I don't think it's necessary to go all the way to that level, but if you are looking for data and hourly data for these different components, it's definitely worth your time to make friends with the resource planners in your jurisdiction or in your community because they have a lot of this. The generation energy piece can either be from the market data or for production simulation. The generation capacity allocation can be from the loss of load probability, loss of load expectation type of modeling. Ancillary services, also from the RTO for whichever region, T&D capacity. There were a few questions in the Q&A around carbon. And really, you will see that's where California is moving. We're really focused our energy policy around reducing greenhouse gas emissions, and that's driving the supply portfolio that sort of changes all of the above. And it also it adds a price of carbon to our evaluation so that when we're doing financial savings and we're saving money during high carbon hours, we get a greater value. One example from generation capacity. This is a forecast for 2020, and what you can see is months and hours, and you see this higher value. And this comes out of a pretty standard resource planning capacity model and shows you what value, and it's really this just after the solar is going down in the summer when loads are high, that's when the value is greatest for generation capacity, given a resource mix in California. One interesting thing that I wanted to show everyone is that these things change. We've been doing a lot of work on SB 100, which recently passed, which specifies a net zero, 100% zero carbon generation portfolio. And when we push it all the way out to 2050, and we find that the least cost solution to that is to add enough storage to kind of reduce that problem in the summer afternoons, and we start to pick up another reliability problem, which is in the winter and overnight. So it's kind of interesting how these things can move over time depending on what your underlying resource portfolio is. The other thing I thought would be interesting to folks is the area. So California has what we call the DRP, or Distribution Resources Planning process, where we've taken the hourly granularity all the way down to area, to very specific distribution planning problems. So you can see the state on the left with these hotspots, and these hotspots are areas where utilities have planned investments to upgrade distribution capacity. And each of those has an hourly profile. So on the top, you can see in the red, you can see those hours that for that particular area, you get some additional value, summer, middle of the day. And then you can think of, in the green, there's a picture of the resources that you're looking at to avoid those. And these are output from a planning tool in the DRP process. And I point this out because this can layer on top of that system. So you can have efficiency that both tackles the local capacity issue as well as the system. And the avoided costs in California kind of include both of those. I wanted to show everyone a picture of the marginal emissions rates. So what this does is it shows for one of the zones in California, the marginal emissions rate. So this is if I reduce load in this hour, how many emissions do I save? It's obviously been a big focus in California. Mostly it's hovering around the heat rate of a combined cycle gas plant with higher and lower, and including zero when we have, particularly in the spring, excess solar, and the marginal unit is a renewable resource without emissions. So this is an area where there's been a number of different approaches, and I think it's new enough that the sort of the theory and approaches for answering this question in California are sort of still an active discussion. So then I just wanted to show just a quick example of how this is working. Where are the emerging applications of time-specific values in California? And one is batteries. And batteries are really an example for any of the dynamic loads. So where I showed that picture in 2004 of the air conditioners are higher value, what we're doing now is looking at dynamics. So this battery storage example shows the battery's charge-discharge profile relative to those system conditions. And I know that LBNL and E3 have also worked on demand response and demand shifting in response to the local conditions. Another hot topic in this area is electric vehicles and electric vehicle charging in terms of response to system conditions, so that we're not just talking about the static energy efficiency anymore, but also all of the dynamics. So that's the quick overview. And I think now we're going to move to Q&A.
Great. Thanks, Snu. And thank you for all of our speakers for participating today. And we've got about 13 minutes for Q&A, and we've had a lot of good questions come in. And so I'm going to start it off by a question to the group. And I think everyone touched on this a little bit, but is this the same, is time-sensitive valuation the same as implementing time-of-use rates? And I'll let David answer that one first.
Can you hear me?
Yep.
Hello?
Yeah, we can hear you.
Okay, sorry. Sorry, you were asking, I was switching headphones, that it was whether this is the same as time-of-use rates or?
That's correct.
Yeah, I think, I would say absolutely not. In fact, if anything, I would say this is sort of well, first of all, I'd say absolutely not. Rates and value, rates in some, anybody who's a utility regulator or utility person on this webinar knows that rates on some level try to mimic the cost to produce that service. But we all know that most Americans don't see time-sensitive rates. In fact, for residential and small commercial, only, depending how you count, only a couple of % of Americans see that rates. More can opt in, many can't. And so I think it's really quite a different issue. The issue here is what's the value to society, either in the cost to produce that power or the value in saving it, regardless of what the rates are. And I think, in fact, there is plenty of ways one can use this work that everybody just described. If you're a utility or a regulator, to say, just as I think Snu was saying, well, look at my air conditioning programs. It doesn't matter what the rates are. This is the value that saving air conditioning energy provides to the system. So I think of them as pretty separate issues, regardless of where your jurisdiction is on the time-of-use rate issue.
Great. Thanks, David. Did any of the other speakers want to chime in on that?
Yeah, I could. This is Ed. I could just add to that. I think it's the valuation component, though, is extremely important for thinking about how to design rates going forward. And just to give you an example, we worked with Xcel Energy in Minnesota, who's anticipating a pretty significant addition of wind energy onto their system over the next decade. So, they did some system modeling to determine what that would mean for their system costs, and we were able to use that information to basically come up with a time-of-use rate that better reflected, the time value of the energy production on the system. With wind being predominantly, at nighttime and certain times of the year increased. So, it's just an example of how you can really take some of these kind of larger system planning exercises and then translate them down into a rate design that better reflects those system costs.
The only other thing that I would add, this is Snu, is that time of use is still averaging. And when you look at the capacity value for both system and distribution, you get just a far fewer number of hours. So the average is going to give you lower than the value. There are retail rate designs like critical peak pricing that are dispatchable for a few hours that are kind of closer. But again, as David said, that's a pricing question as opposed to overall resource value question.
Great, thanks, Snu. So we had a lot of questions come in about carbon and about calculating it and the impact and how to consider it in time-sensitive valuation. And one of them that came through is you focused on hourly variation in electricity prices and value, but what about hourly variation in environmental benefits of efficiency? And I'll hand that one to Judd to answer first, and then I think maybe Snoo or Ed, you might want to chime in on that as well.
Sure. Thanks, Natalie. So absolutely, that's an important question that I'm happy to point people to academic work on, and I'm sure Snoo and Ed and others will have non-academic work to point out. It's definitely true that the avoided emissions vary hour to hour in an important way, and that variation is changing as the grid changes. What we did find in our paper, and we talk about this in the printed version of the paper, right now that variation is actually small relative to the variation in private electricity values, which when you're an environmental economist, you're not used to writing papers that say environmental things aren't relatively important. And I certainly would never say that that's not important. That's very important. But in the context of our paper, we found that when we think purely about time, the variation in generation costs and scarcity value of electricity is so large that it actually really overwhelms that variation in carbon costs. Of course, that depends on what value you want to use for the costs of carbon. And with a sufficiently high cost of carbon, that statement that I made is no longer true. I think that's where I would leave that. And I'm happy to point people to specific academic work. Meredith Fowley and Duncan Calloway at UC Berkeley have some really great work on emissions variation over time and over space. My colleague Josh Graf-Ziven here at UC San Diego also has some nice work on avoided emissions cost variation over time.
Great, thanks, Judd. One of our other questions that came in.
Hey, sorry, Natalie, can I just add to the last one? Say, and this isn't about carbon, it's about any emissions or about efficiency more broadly. Remember, it's not just is it coal, is it nuclear, is it wind, is it gas at the margin? That's obviously important to these, but that's number one of the issues to analyze. Two, what's the heat rate of the plant at the margin? And most systems save their highest heat rate, least energy efficient resources for peak periods, logically enough. And three, there's in a congested system, there's T&D losses. That I squared R loss goes up because that square goes up a lot at peak. In parts of California, it's over 10% just T&D losses at peak. So just want to say it's more than whenever you do the environmental analysis, you gotta, or the efficiency analysis, you gotta look at all that stuff.
Thanks, David. So another question that came through, there's lots of cost-effective energy efficiency that we are not yet realizing, so why overcomplicate things with time-sensitive valuation? So I don't know who wants to jump in on that one first. I think we heard a lot from all of our speakers about the importance of time-sensitive valuation, but I don't know if anyone has anything they'd like to add to that.
Well, one could flip it and say, because there is so much to do, one should aim for the bullseye. And say with however much society wants to invest in energy efficiency, public and private and utility sources and all the other ways we invest in efficiency, let's focus on the bullseye where we're getting the most bang for the buck. And again, I think all the speakers who spoke showed that you get a lot, when it comes to efficiency, you get a lot more bang for your buck at the right time of day, and therefore, whether it's air conditioning or whatever it is, but was it your slides, Stu, with the outdoor, or a couple of you folks, outdoor lighting is valuable, but air conditioning is closer to the bullseye. So to me, it stretches out what resources we have.
Yeah, I guess the other thing I would say, just this new, is that the level of incentives and cost effectiveness of different programs, the way we do it, air conditioning or on-peak measures just may not be top of mind and may not be in the portfolio. So again, I guess that's another way of saying, it's worth it because then you can target measures that are sort of across all of the most important measures.
Yeah, and I would just add, I mean, in an ideal world, we'd have unlimited funding to spend on energy efficiency, but in reality, a lot of times that's not the case. So when we have to prioritize, it can be helpful to, like Dave said, get the most bang for your buck.
Great, thank you. And I think this might end up being our last question. What steps should be taken now to anticipate future changes in energy value of energy efficiency? And I guess we'll let Ed start that one off, and then we can go through the rest of our speakers for their thoughts on that.
Could you just repeat that question one more time, Natalie?
Oh, sure. What steps should be taken now to anticipate future changes in energy value of efficiency?
Right. Well, I think, you know, I sort of alluded to this earlier, but I think to the extent that, you know, we can be somewhat forward-looking and anticipating some of these changes and really linking up the planning of energy efficiency deployment with sort of the system resource planning, I think that's all a good thing. And trying to think more, I guess, holistically about what the grid will look like in 5 or 10 years, and not necessarily just what it looks like today. And that way we can be really tailoring our delivery of efficiency in a way that's forward-looking and not just kind of status quo.
This is Snu. I would say when I look at it, just at least in terms of the types of analyses that we've been asked to do, is really thinking about the dynamic effects and features. And I think David mentioned this in his remarks around, you know, things like pre-cooling, things like energy management systems. And so, you know, even if you're evaluating a static efficiency portfolio today, taking the time-specific approach is sort of like a warm-up lap for being able to look at some of those more dynamic type of features that I feel like are coming, you know, through a number of ways.
So I'll jump in there as well. This is Judd. You know, I obviously have a slightly different perspective than everyone else, but I think one thing we can do is we can try and set up opportunities for smart monitoring and evaluation that will help us design effective programs and improve programs over time. So the world is changing both in terms of renewables integration and also because we now have this wealth of really granular energy consumption data. Let's have a bunch of partnerships between smart academics and utilities and others who want to go out and really study that in detail and figure out how behavior works and how these markets work and how we can design successful programs.
Thanks, Judd. David, did you want to have the last word on that?
I'll just say all of the above. I agree with everybody on the panel, and I think on this, so the analysis, and Natalie, you led a lot of this work, is key, and then sort of anticipating, which I think is very easy, achievable, anticipating what the analysis will find when we look at, for us, it's a research program, for somebody else, it's a deployment of a utility incentives. How do you reshape those as that analysis gets more sophisticated? So I think there's plenty of work to do, as everybody just said.
Great, thank you. And that we're at the end of our time, and I appreciate everyone getting on the line, and thank you to all of our presenters again. As I said, this information, a recording of the webinar and the slides will be available on a Berkeley Lab website. I can send that link out, and I look forward to future conversations and research on this moving forward. Thanks, everyone.